Hello students, this is Dr. Ben, and I'd like to work out a problem from Chapter 4 that is on the second part of the hand-graded homework assignment. And this is problem 4.24 and involves a block sliding down a frictionless inclined plane. And we want to analyze this problem from both the forces perspective and the motion perspective. So the first two parts of the problem are about the forces element. And so we need to start by drawing a force diagram for this block. So I have it drawn at some arbitrary point on the inclined plane, and we can use a force diagram to draw the forces that are acting on the block. So there will be a normal force and a weight force. And if we remember that for the plane angle being equal to theta, that the angle that the weight makes with the extension of the y-axis is also the same angle. And we'll use a coordinate system that is tilted with the plane because it's more convenient. So I'll call x pointing down the hill and y perpendicular to the hill. All right, so in the first part of the problem, we are asked to find the net force on the block after it's released. So in the y direction, there is no motion. And then by Newton's first law, we would have that the net force in the y direction is simply equal to 0. But in the x direction, the block will speed up as it goes down the hill, so there's going to be an acceleration parallel to the incline, and so the net force would be equal to the component of the weight force that points down the hill, because the normal force only points in the y direction. So the net force in the x direction would be given by m times g times the sine of theta, because we want to have the shadow of the weight force that is parallel to the incline. So that side of the triangle is opposite to the angle theta. And if we put in the numbers that are given, the mass is 10 kilograms, g 9.81 meters per second squared, 55 degrees for the angle, we get 80.4 newtons as the net force in the x direction. Okay, part B then says what is the acceleration of the block. So Newton's second law would tell us that the acceleration is equal to the net force divided by the mass. So in the y direction, the acceleration is equal to 0. And in the x direction, the acceleration will be equal to the net force in the x direction divided by the mass. So that's simply the 80.4 newtons that we found divided by the mass, that's 10 kilograms. So that gives us 8.04 meters per second squared. All right, so there's part A of the problem and part B of the problem. That was the forces perspective. And the rest of the problem is all about looking at the block's motion as it slides down the hill. So in the first part of the next, as part C, we're asked to find out how long the block takes to obtain a final speed of 10 meters per second. All right, so to do the motion part of the problem, we need to switch our perspective and draw a pictorial representation. So the force diagram is the tool that we use for analyzing the forces, and the pictorial representation is the tool that we use for analyzing the motion. So we need to have an initial point and a final point, and we'll put the origin of our coordinate system at the initial point, and we'll call the positive x direction down the hill. We don't even need a y direction for the motion because there's only motion along the plane. And I'll go ahead and define my kinematic variables. So I would have x sub I, v sub I, and t sub I. And I have xf, vf, and t sub f. and we also have an acceleration in the x direction. So we can make a table of what we know. So the value of xi is equal to 0. The block starts from rest at the time equals 0. The value of x final we don't know, but the value of v final we're given to be 10 meters per second. And the value of a sub x we found in part B of the problem was 8.04 meters per second. And what we want to find, at least in part C, is the value of t sub f, which is the time that it takes for the block to get down the hill. All right, so we need to use our kinematic equations to work on this next part. And since we want to find out something about time, it makes sense to use one of the kinematic equations that has time in it to try to solve the problem in one step. And since we know something about the initial and the final velocity, the second kinematic equation would probably be the most useful. So that would say that v final equals v initial plus the acceleration in the x direction times t final minus t initial. And like always, let's cross out the variables that equal 0 before we do any algebra. So the initial velocity is 0 and the initial time is 0. So that gives us that Vf is equal to a sub x times Tf. And we can see that the algebra is very simple in this problem, that to find the value of t, we just cross multiply and we get V sub f divided by a sub x. And if we plug in the numbers that were given in the problem, we have 10 meters per second divided by 8.04 meters per second squared, and that gives us 1.24 seconds. So that's how long it takes the block to increase its speed to 10 meters per second given the particular angle of the ramp. All right, so the last two parts of the problem are more conceptual. In part D, we're asked to draw a motion diagram. So we remember that a motion diagram represents the motion at equally spaced intervals of time. So we'll draw that motion diagram along a diagonal line. Oops. So we'll have a diagonal line, and we want to put points that are equally spaced in time. And so since the object speeds up as it goes down the hill, the dots need to get further apart. And then to complete the motion diagram, I add the velocity arrows. So I simply connect the dots with velocity arrows like we learned about in chapter 3. And then on top, I draw the acceleration arrow because the acceleration is in the direction of the motion. All right, and then in step E, we want to make a graph of the x velocity versus time. So we'll do that on a set of axes. We'll put time on the horizontal axis, and we'll put the velocity in the x direction on the vertical axis. So the block starts from rest, so that would be v equals 0, and it increases its speed at a steady pace because the acceleration is equal to a constant. And we remember from chapter 3 that we learned that the slope on a velocity versus time graph gives us the value of the acceleration. So the acceleration in our problem is a positive constant, so that means that the slope needs to be a positive constant. In the shape of a figure that has a positive constant slope would be a diagonal straight line that is moving upwards. All right, so there you have it. We analyzed the problem using forces first of all to find out the acceleration, and then we analyze the problem using motion to find something about the time and how the velocity changed.